Okay, so imagine a future where type 1 diabetes is reversible. Like you wouldn't need those daily insulin injections anymore.
Hmm.
That's what this new research in science advances is pointing towards.
Yeah.
We're diving deep into this study today, and we'll see how close we actually might be to this future, a cure for type 1 diabetes.
It is exciting research, that's for sure. I think one of the biggest hurdles that's always been there is islet transplantation.
Right.
Even if you can find donor islets, getting those islets to survive long term, it's been a challenge.
Right. It's like, it's not as simple as just, popping a new battery in or something.
Yeah.
We're talking about living tissue here.
Exactly.
They need that very specific environment to function.
Precisely. And, the current way of doing things, transplanting them into the liver, it's not ideal. Islets aren't naturally supposed to be there, so they just don't really integrate well.
Right.
And then, of course, you have the whole issue of lifelong immunosuppression.
Right. To avoid rejection, which of course comes with its own set of risks.
Yeah.
So this new study, they're trying a different approach.
They did. It's all based on these fascinating cells called reprogrammed vascular endothelial cells, or R-VECs for short.
R-VECs.
Yeah, so they essentially took cells that weren't blood vessel cells and through, some genetic engineering, turned them into cells that actually can build blood vessels.
So they kind of reprogram them, like giving them a new job description.
Yeah, that's a good way to put it. And the cool thing is these R-VECs, they don't just build any old blood vessels.
Yeah.
They can create vasculature that is very specific to the tissue that they're in.
Okay.
So in this case, they essentially built a network of blood vessels that mimic those naturally found in the pancreas.
Wow. Okay, that's cool. But why is building blood vessels such a big deal for islet transplantation? Isn't it enough to just get the islets in there?
It's not enough at all. Think about it like this. If you tried to build a city,
Yeah.
but you didn't build any roads,
Right.
like supplies can't get in, waste can't get out, nothing's functioning.
Nothing works.
Got it.
Blood vessels are basically the islet's lifeline.
Okay.
And past attempts at transplanting islets under the skin failed, precisely because they just couldn't get good vascularization there.
So these R-VECs, they're like coming in as city planners and just making sure that this new islet city thrives.
Exactly. And here's the really cool part. The blood vessels that these engineered cells created were actually larger in diameter than the natural capillaries usually found in islets.
Wow.
Meaning more blood flow, better nutrient delivery, and likely a big reason why these islets did so well.
Okay, so we've got the islets. They've got their custom-built superhighway system. We put them under the skin. Did it work? Did it actually help with diabetes?
In mice, the results were really incredible. So they took these R-VEC enhanced islets, transplanted them subcutaneously, and these mice who had hyperglycemia before, their blood sugar levels went back to a normal range.
So hold on, their diabetes was basically reversed, just like that.
Yeah, just like that. And they wanted to be sure, so they tested for human insulin in the mice.
Okay.
And it was there.
Yeah.
Meaning that these transplanted islets were actively producing insulin, and they were doing their job.
Wow, that is huge. I'm guessing they didn't just stop there. Did they do anything to prove this wasn't just some temporary fix?
Oh, yeah. They went back in. They removed those islet grafts.
Uh-huh.
Guess what happened? The mice went right back to being hyperglycemic.
Oh, wow.
No more insulin, no more regulated blood sugar.
Oh, okay.
So that's proof. It was those islets that were responsible.
Wow.
Yeah.
Okay, my mind is still blown with these results in mice. But before we get ahead of ourselves and start talking about human cures, let's go back to these R-VECs for a second. How do scientists actually make these? It sounds like something out of a sci-fi movie.
It is pretty high tech, but it's actually really elegant when you get down to it.
Mm-hmm.
You see, all the cells in our body start with the same basic blueprint, which is our DNA. But as cells develop, certain genes get turned on or off, and this guides them to become a specific cell type.
So like a master switchboard that decides if a cell becomes a skin cell or a heart cell or whatever.
Exactly. And scientists have figured out how to manipulate this switchboard.
Wow.
In the case of R-VECs, they focused on this gene called ETV2.
ETV2.
And this gene is essentially the master controller for blood vessel development.
So by introducing ETV2 into cells that weren't destined to be blood vessel cells, they essentially tricked them into becoming these expert vessel builders.
That's the gist of it, yeah. And what's even more impressive is that they can actually fine-tune these R-VECs
Oh, okay.
to create blood vessels that are tailor-made for specific organs.
So they're not just cranking out generic blood vessels, they're creating a vascular system that's specifically designed for the needs of these transplanted islets.
Exactly. Remember how we talked about those larger-than-normal blood vessels in the mouse study?
Yeah.
Well, that wasn't random. The R-VECs were programmed to build those superhighways. And they do such a good job of integrating with the host circulatory system that they effectively created a lifeline that allowed these islets to flourish.
Okay, I'm starting to get the bigger picture here, but walk me through exactly how these R-VECs work their magic when you actually do this transplantation under the skin.
It's all about teamwork. Think about it like this. You're not just transplanting the islets, you're transplanting them with their own personal construction crew. The islets provide the insulin-producing power.
Right.
And the R-VECs provide the infrastructure.
So while the islets are settling into their new digs under the skin, the R-VECs are busy building a vascular network to support them.
Exactly. It's like creating a miniature ecosystem right there under the skin. And what's really remarkable is these R-VECs don't just play a supporting role. They're really the stars of the show when it comes to building blood vessels for these transplanted islets.
So they're not just lending a helping hand, they're doing the heavy lifting when it comes to creating that crucial blood supply.
Exactly. In fact, the study showed that the R-VECs contributed more to the islet's vascularization than the host's own endothelial cells. They really take charge. They create this network that looks almost identical to the intricate vasculature found in the natural pancreas.
You know, this whole idea of transplanting islets under the skin always seemed like such a long shot to me because of that whole vascularization issue. But it seems like these R-VECs just flipped the script entirely.
Yeah, they really have. It's like turning a weakness into a strength.
Yeah.
And that's the beauty of innovative thinking in science. We're constantly finding new ways to overcome what seem like these insurmountable challenges.
It all sounds incredibly promising, but I know you're not going to let me get away with skipping over the potential hurdles here. What are some of the big questions that still need to be answered before we can even start talking about using this in humans?
Well, first and foremost, we need to make sure this approach is safe and effective beyond mice. We need to see how it works in larger animals, ones that have physiology closer to our own.
So kind of like a stepping stone before going to human trials.
Exactly, yeah.
Yeah.
We also need to optimize the technique for human islet cells.
Right.
There might be subtle differences in how mouse and human islets respond to these engineered R-VECs.
That makes sense. You wouldn't want to rush into human trials without ironing out those details.
Of course not. And of course, the elephant in the room with any kind of transplantation is immunosuppression.
Right.
It's kind of a necessary evil to prevent rejection, but the side effects, they can be pretty rough.
Yeah.
So finding ways to minimize or even eliminate the need for that is a huge priority.
I'm guessing that's not an easy problem to solve. How are researchers thinking about tackling that challenge?
One promising avenue is encapsulation. Imagine if you could create a sort of invisibility cloak for these transplanted islets, shielding them from the host's immune system.
So the immune system wouldn't even see the islets as foreign invaders.
Exactly, yeah. And there are a couple ways to do this. Some researchers are exploring biocompatible materials that can actually encapsulate the islets, while others are looking at ways to modify the islets themselves to make them less immunogenic.
So it's a two-pronged approach. Either hide the islets completely or make them look so familiar that the immune system just doesn't even notice them.
Precisely. And if we can crack this code, it would be huge, not just for islet transplantation, but for all kinds of cell-based therapies.
Yeah, we're talking about a potential paradigm shift in medicine. It's pretty mind-blowing to think about the possibilities.
It is. And it really is a testament to the power of just scientific curiosity,
Right.
Like, who would have thought that we could reprogram cells to build custom blood vessels? Sounds like science fiction, but it's becoming a reality.
It is. This has been such a fascinating journey so far. We've gone from, the basic science of R-VECs to this, intricate dance of vascularization and the potential for revolutionizing transplantation. What else is there to uncover in this deep dive? We've spent the last two parts really getting into the science of all this, but I think it's important to step back and think about the bigger picture for a second.
Right.
We're talking about potentially, life-changing treatments, and that always comes with some ethical questions.
Yeah, absolutely. Whenever we talk about medical breakthroughs, especially something like this, that has the potential to really tackle a chronic condition like type 1 diabetes,
Right.
we have to consider all those implications, the ethical side of things as well.
So where do we even begin with something like that? What are some of the ethical concerns that come up with this kind of research?
Well, I think a good place to start is the source of these islet cells themselves.
Yeah.
In this study, they used human cells,
Mm.
which is incredibly promising in terms of actually translating this into a therapy for people. But, that also brings up the question of where those cells are coming from.
Right.
And how do we make sure that the sourcing and the consent was all done ethically?
It's a good reminder that, even with all these amazing scientific advancements, we're still dealing with human tissues and lives here.
Yeah.
We can't just get caught up in the cool science and forget about the human element.
Yeah, you're absolutely right. And there's also, the issue of unintended consequences.
Right.
We're still learning about the long-term effects of manipulating cells.
Right.
And while, the potential benefits are huge, we have to be really cautious and make sure that we're not accidentally creating new problems down the line.
Right. It's like that old saying, with great power comes great responsibility, right?
Yeah.
We have this incredible ability now to manipulate cells,
Yeah.
but we need to make sure we're wielding that power very carefully and thoughtfully.
Yeah, I couldn't have said it better myself. And then there's the question of access.
Right.
If and when this treatment becomes a reality, how do we make sure that it's available to everyone who needs it?
Yeah.
Regardless of their income or where they live. We don't want to create a system where only the privileged few can actually benefit from these kinds of breakthroughs.
That's such an important point. It's easy to get caught up in the excitement of a potential cure, but we have to remember all these, the systemic issues that could prevent some people from benefiting from it equally.
Absolutely. And finally, we also have to, be mindful of the impact that research like this has on people who are living with type 1 diabetes right now.
Mm.
This study, it offers a glimmer of hope, but, we have to manage those expectations. We don't want to give people false hope or make them think that a cure is right around the corner.
Yeah.
When the reality is, it could still be years away.
Right. It's a delicate balance.
Right.
And we want to celebrate the progress, fuel that optimism, but we also need to be realistic about the challenges, the timeline.
Yeah, I think that's right. But even if a cure isn't, right around the corner, this research still represents a big step forward.
Right.
It gives us a whole new way of thinking about how we treat type 1 diabetes.
Right.
One that focuses on, not just managing the symptoms, but actually addressing the root cause of the disease.
And that shift in perspective is so powerful. Just imagine a future where instead of constantly monitoring your blood sugar and worrying about complications, people can just live their lives free from that burden.
Yeah, it's a future worth striving for, And studies like this one with its innovative approach and the impressive results that they've shown, it really does give us reason to believe that future is possible.
This whole deep dive has been a whirlwind. We've gone from reprogrammed cells to custom-built blood vessels to the potential to just revolutionize how we treat type 1 diabetes. It's amazing to think that this is all happening right now,
Yeah, it really highlights how fast science is moving. Who knows what other breakthroughs are just around the corner.
It really is exciting. Well, that about wraps up our deep dive into this fascinating stem cell research.
Yeah.
We've covered a lot of ground. We talked about, the intricate science behind it, the ethical considerations, the hope it brings for people with type 1 diabetes.
Yeah, it's been great exploring this with you. And to our listener, we hope you walk away from this with a deeper understanding of this research and the potential it has.
Absolutely. And as always, we encourage you to stay curious, keep asking questions. The world of science is full of surprises, and who knows, you might just be the one to uncover the next big breakthrough. Until next time.